So thank you so much for having me. Thank you to the organizers. I'm very excited to be here, and I'm going to take this now more to the macro side. This talk was, and I'm very lucky to be talking after David, because I can really build on everything he explained, and he explained it much better than I could explain it. So I'm going to give a little bit of an overview talk, which is based on two papers. One which is more recent, which is joint work with Jan Zemlitschka, and one paper which is already a bit older, but when we were starting out using this deep learning-based method, which is joint work with Luca Gigauf and Simon Scheidiger. And so what do we want to do? So there's a class of economic models with heterogeneous agents and aggregate risk, but we really want to take the risk seriously. Examples are models with large shocks, or where we want to think about asset prices. And in these cases, we do not want to linearize or use perturbation solutions, but instead, we really want to know the global solution. What do I mean with the global solution? So in these models, there's a state of the economy, which is X. It typically includes some stochastic components, like we wake up and we see, oh, the world is productive today, oh, the world is not so productive today, maybe the sun shines. And then there's a distribution which describes what situation is the economy in. For example, typically it could include the wealth distribution, or there could be many assets, and then this wealth distribution would shift around as a result of those shocks. And we want to know, for all those possible states, what does the economy do? What do households do? What are the prices? So for example, what does each household consume? How much do they save? If there are different assets, how much stocks do they buy? How much bonds do they buy? How much do they work? And these are the functions F. So X are not the state of the economy, and F are the policy and price functions. And computing a global solution means computing those functions such that they are consistent with the equilibrium. And what does it mean, consistent with the equilibrium? It means what a household does has to be optimal for the household, what the firm does have to be optimal for the firm, and we can often describe this as a set of equations. And I have to apologize because my notation is inconsistent with David's notation. So my G is his F, my F is his G. I'm so sorry. I think you are more standard, so I should change it.
I don't know that.
So in any case, we search these functions which fulfill those functional equations, and this becomes hard. It becomes hard, especially when the X becomes high dimensional, and the functions become nonlinear. Because now we want to approximate something flexible on a high dimensional domain, and this naturally arises in many settings, but among others, when we are thinking about overlapping generation models. I'm just going to mention those because that's what I'm presenting in the slides, which is a model that we think about the aging. So we have households of different age groups. And then if we have, for example, 60 age groups, our state space includes the wealth of all those 60 age groups in the economy, which is then already automatically high dimensional. And to overcome this challenge here, there's a kind of new strand of literature and that uses deep learning to try to approximate those functions. And I'm going to focus on two papers. And the first one is already the working paper that's back to spring 2019. It's been well published. This was the first work I did. And then second, more recently, we tried to innovate on the places where we still see some challenges. I focus on these two papers because that's the one I work on and the one that I know best. But I also want to point out that there are other papers that I really recommend having a look at, and I'm really honored to present with people in this room who really are pushing the frontier. All right, so what's the idea? The idea is, okay, we're searching for this F, so that for all X, these equilibrium conditions are fulfilled. Now what we want to do, we want to use a neural network N with parameters rho to approximate these functions. But how can we know, how can we get our neural network to do what we want it to do? We have to approximate those functions. In the standard deep learning, you would have those label data inputs with known outputs, and you would train a neural network to predict those, maybe using a mean squared error. And in that settings, this availability of label data is often a bottleneck. But we cannot do this because we don't know those functions at. We don't know the true output for any input. That's exactly what we want to find out. But, and this was kind of one of the main insights of the first paper, we do not need those. Because all we need is a measure that tells us, is the function good or bad? And how do I have to adjust the parameters of the neural network to get better at approximating these functions? And we have such a measure because those functions we want are exactly characterized by a set of equations, which I know. So I can just take the function, plug it in. If it's 0, good. If not, make it closer to 0. And in that way now, we kind of know that for all states action sets to hold, so we can essentially train the neural network on a large, huge, infinite amount of data. In practice, of course, we cannot train it for all x. Because we're talking about high dimensions, what does all x mean? But in practice, we also do not care about all x. What we care about is those states of the world when we later take our solution, our policy functions, and we simulate the model forward, drawing exogenous shocks. There will be a certain set of ergodic states where the economy lives, and certain states which will never be reached. What we want is our approximation to be good in those states. So what do? And we iterate between simulating from the policy we have, collecting those states, then training the neural network to get better on fulfilling the conditions on those states. And now we have new policies, new prices. So then again, we simulate new states and so on. Of course, initially our policies are random. So we not simulate what we call the ergodic set of states. This is not where the economy really lives once you solve the model. But as we proceed, as we get better and better policies, we also automatically converge to training the neural network exactly where it matters, namely on the ergodic set of states. So this is now the basic idea. Let's become a little bit more concrete. And I'm going to present you a kind of simple overlapping generation model to illustrate how this works. But it's not that simple because I need to put in some complications it must be rich enough to show all that I want to show you. So the idea is you have one representative firm that produces capital K and labor L. And Z is productivity. That's a stochastic shock. So we wake up, we see we are productive, not productive. This follows an AR1 process. And then we also assume that the productivity will affect the depreciation of capital. So when we are not productive, also our capital will be less valuable. That adds kind of extra risk to holding capital as an asset. There are two assets households can trade, bonds and capital. Bonds are risk-free bond period assets. So if I buy a bond today, I get 1 unit tomorrow. If I buy 1 unit of capital today, what I get tomorrow depends on the shock, like if it's a good state or a bad state. And households live for 32 periods. So we think of one model period for 2 years. And they can trade bonds without adjustment costs, and they trade capital. There are some adjustment costs making capital a little bit less liquid than the bond. And the budget constraint of households is given by they consume, they get labor income, they get their payouts of their assets, then they spend on how much to buy of each of the two assets. And they do all of that optimally to maximize their expected discounted lifetime income. So they maximize this, which is a kind of very standard macro expression. Every period they get utility from consumption, which is concave, and they sum it up over all their remaining life. And because it's concave, they kind of prefer to consume smoothly. So instead of eating 0 breads and 2 breads every second day, they prefer to eat 1, 1, 1, which is what they are trying to do with their assets. And yeah, so how does an equilibrium look like in this setting? An equilibrium means that markets are too clear. We have two markets for capital and for bond. Capital market clearing here is kind of easy to ensure because we assume the price of capital is 1. So we can just sum up the capital that households have, and this will give us the aggregate capital. Bond market clearing is a bit more tricky. We need to make sure that in every state, the price is such that supply equals demand. And then firms optimize, which is also trivial here. And then the household's choices have to be optimal subject to the borrowing constraints, which gives us a set of Karush-Kuntaka conditions for each generation and each asset. So we'll have the 64 Karush-Kuntaka condition and this market clearing condition to enforce. So how do we want to handle this? So the state of the economy, X, includes the shock, the productivity shock, then the distribution of capital across age groups, and the distribution of bonds across age group. And because prices depend on the whole distribution, the decision of households will also depend on this whole distribution. And that's what makes this kind of high dimensional, what makes it useful for us to use neural networks. So we want to find those functions which tell us, depending on the state, how much do I sell for the next period. And I'm going to end the price of the bond. And we're going to approximate this to the neural network. And then we're going to train the neural network to minimize the error in the optimality condition on capital, in the optimality condition on bonds, and market clearing for the bond market. These are the three optimality conditions, and I want all of those errors to be zero. And this was how we did it in the first paper, and we showed that it works kind of well in some settings. However, there were still challenges remaining, and in particular, it's a bit unsatisfactory that here we are implicitly trading off between fulfilling the market clearing condition, meaning the condition that supply is equal to demand, with household optimality. Because number one, it makes it harder for me as an economist to say, did I solve the model? Like, I have some error, maybe it's 1%. Is it good enough or not? Does it affect my result or not? Like, what do I need to do economics? And second, this is a simulation-based method, because and that's an important aspect, I think, in high dimensions, because we want to solve it really on those relevant states in high dimensions. We, for example, would solve it on a hypercube. It would be wasted effort almost everywhere, right? So we simulate from a policy that is not consistent with market clearing, it means the states that I sampled are also not consistent with market clearing. And then enforcing market clearing on those states may actually push the updates in the wrong direction. Because if I wake up with too much bonds, then even the correct policy will predict too much bonds in the evening. So how do we do this? And the first thing we do is to say, well, we already know that markets have to clear. So why make the neural network learn something which we know to be true? And we can, in fact, just devise a neural network that, by design, always predicts only policies consistent with market clearing. And depending on the model, this can be done easily or a bit more complicated. But essentially, we can do a two-step procedure. We have an initial output, and we transform it with what we call a market clearing layer. And then we take this together as a neural network. And now the prediction is always consistent with market clearing, and we can take out this term of the loss function because by construction is satisfied. And then the optimality conditions are the only remaining terms in the loss function. And we can interpret it more easily, and we simulate only from correct policies. Yes.
Is this a similar idea to what people sometimes call physics-informed neural network, where you use the constraints that you want the model to satisfy as you incorporate it into the structure?
Yeah, I think you could call it. So this is in the broader scheme of things. There's the idea that there are some things you can take one-to-one from math or from computer science, but also economics is special. Like, our problems are different. So there are some things we cannot take one-to-one, and what we want to do is to find out how do we have to modify things, how do we have to change things to have specialized algorithms to our model. And here what we are doing is we are encoding market clearing directly into the neural network. For example, Marlon has a paper where he encodes symmetry properties. It's a beautiful paper directly into the neural network. Also, Jonathan has very nice papers with similar ideas. So this is by no means the only one, but I think it goes on in this direction that we want to bias the neural network in what we know are the economically correct solutions. And they're not forced to train something which we know. And here we do this. Okay, secondly, another thing that we realized, that we had to realize, is that single asset models are kind of easy to solve. It's kind of easy to figure out how much to consume and how much to sell. But it's much harder to figure out how much to sell in different assets. And that has a reason. The reason is that kind of the first order conditions for many assets are just worst condition. So the error we need in the equilibrium conditions to pin down those choices accurately is just much lower than what we need to pin down the overall consumption saving choice. But if we cannot kind of pin down the decomposition in different assets, remember we start with the wrong policy, we start with high errors. So our policies are just fluctuating around like crazy, and then we simulate you will simulate in different regions of the state space all the time, and training will become very hard. So what do? You realize that every L asset model essentially nests an n-1 asset model, because you can simply set the extra asset to 0 with tight borrowing constraints at 0 and set the supply to 0. If no one can borrow and the aggregate supply is 0, you know that the solution is that nobody holds any of these assets. So now we are essentially back to the one asset model. We can solve that, and they can use that solution to predict the price for the bond for the next asset that would be the equilibrium price. You would introduce an infinitesimal amount of that asset. Because that solution without the asset is a very good approximation to the model with a tiny amount of that asset. And then we can predict the price, and once we have the price, we can start slowly introducing the next asset in the economy. And in that way, at every point, we'll have a very good starting guess for our policy and price functions, and we will be able to remain at a precise solution that will never lose the ability to pin down this portfolio choice. Yes.
Have you tried it where you include the amount of liquidity as an input into the neural net? And so then in each training step, you draw a liquidity, and then you kind of simulate it from where you are, then you go back, you draw another liquidity. Have you tried that? Do you know how well that works relative to the homotopy?
So I haven't tried it, so I think we tried it during the homotopy. So I guess what you're saying is that we would anyway want to start out with a single asset model. On that, I'm kind of positive. I don't think that we would want to start out with the two asset model. But then once we do this kind of transition, it would be kind of sped up by the new network realizing how to adjust the policy. So I think you're probably right that this would be valuable. And we have tried with models where the liquidity is kind of in itself in AR1, for example. And then we of course had to include it in the state space. And we did that, but it's not exactly what you're saying. So definitely a good idea. Then we slowly increase the supply until we reach the demand, the supply we want to have. So let's see how it works. So we start out with step 1. We set the bond supply to 0. We set the borrowing constraint to 0. Now our neural network essentially only predicts capital, and the only optimality condition we have is on capital. Now we solve the model, and here what you see is the loss. It's a mean squared error, so it goes to 10 to the minus 6. Here in the middle on the top, you see the asset distribution across age groups when we simulate the model from the policies. So you can see this is a very typical picture. The mean is in the solid line, and then you have the first and 90th percentile in the dashed line. It's that households save up for retirement and they use up their assets when they retire. And this shows the relative consumption error in the first order condition. And you can see it's around 0.1% on average and below 1% in the 90th percentile of the error. So for this single asset model, there's a good error. And what you can see on the bottom is the left-hand side and the right-hand side of the first order condition, not including the multiplier. And here you can see the difference between them, which is essentially the Kirsch-Kuntaka multiplier, and it's positive, meaning houses are constrained. So in this model, on average, young houses are constrained. They would like to borrow because they face increasing income over the life cycle, but by construction of our model, they cannot. And then once they get richer, they start saving and they consume from retirement. This is the first step. This is the single asset model, which is kind of easy to do. Now we want to use that solution to price the bond. How do we do this? We basically solve the first order condition for the bond price, and then the agent that would buy it, if you introduce a tiny amount, is exactly the household who would be willing to pay the largest price. So we just compute the implied bond price for each household, and then we take the max. This gives us, so to speak, a closed form solution for the bond price in the limit where we now introduce a tiny amount of bond. And now we can train a neural network in a supervised way to additionally learn the bond price. Notice this still depends on the state of the economy. So it's not a number, it's a function. So we train it by including this objective into the loss function, and it's still a single asset model. So we're not releasing the bond policies yet. We first pre-train the price. You can see the policies don't change. And here you can see the left-hand side of the Euler equation and the right-hand side for the bond, and you can again see the multiplier. And here you can essentially see what I already said is that all age groups are constrained because this is the kind of the limit of 0 amount of bond. And exactly at that price which we trained, only one age group would be unconstrained, which is exactly the one which we use to price the bond of, the one which would be in most urgent need to buy it. Now we have a good starting gate also for the price, and we have a good starting gate for the policies. So now we start by slowly introducing the second asset into the economy. And because we have these market clearing layers, you don't need to worry about market clearing. So market clearing will already be satisfied, and we just now train a neural network to satisfy both optimality conditions. And so in blue here, you will see the distribution of bond holdings over simulations. So you see in the beginning, it's zero, it's a flat line. And here you see the consumption over age groups. And here you see the errors in the optimality condition for bond and capital. And we start introducing the bond slowly. And here you can see the loss function. So you see it goes up a bit. But key of this method is that it should never go up to like 10 to the minus 3 or 10 to the minus 4. Because then the choice between bond and capital would not be pinned down and basically the algorithm would crash. So we do this slowly enough to slowly introduce more and more bonds until you reach the level you want to reach. And you can see that in the end of training, the errors are low, so on average below 0.1%. Optimality error in the households, optimality conditions, and on average below 1%. Yeah, so that's how it works. So in the paper we have a richer model with housing and 3 assets and so on, and we do some more economics. But on the method side, which is what I want to focus on here, this is kind of what we did. So the basic idea is first to train the neural network directly to satisfy the equilibrium conditions, because this is in fact the measure that we as economists would use to say, is this a good policy or not? So why not directly give that to the neural network? Secondly, train on the simulated path, which I found very important, especially in high dimensions. And then for portfolio choice, there are the specific problems, but portfolio choice are particularly interesting because it's one of those applications where those global methods are needed and we do not want to linearize when we care about those large shocks. And that's why kind of we want to make progress here. And if you are interested, I also want to say, of course, now you cannot remember those links, but we have a simple Jupyter notebook tutorials. If you go on my webpage and you go on teaching, you can find them. And then in TensorFlow, we will put them to Jack soon. But just if you're interested to check it out. Thank you so much. Thank you.